Okay. Even though this part's not on your slide, but let's make our understanding of the Bayesian game complete by also looking at the continuum of action version of the game. Now, so now let's set out the assumption of the game now. We have two herders like before, but herder one has private information about his value of grazing sheep. Why herder 2 doesn't? Does not. Okay. The value for herder 1 is now v1 as a function of q1, q2, but also t. Now, his type. Alright? Equals t minus q1. I'm worried that you might not see anything from that anyway. So let's change that. q1 plus q2. Now, doesn't make things better. Y for herder 2, it remains the same like before. 120 minus q1 plus q2 still. Now, one thing worth reminding at this point, remember the type of the herder does not only affect his payoff or the value per sheep directly via t standing alone here, but also via q1. No? So if he's like kind of entrepreneur type risk taker, then probably he would raise more sheep or something like that. No? Just an example. Okay? And we see that clearer along the way when we derive the best response. Now, what makes a difference with t? We could have th, like high, equals 130 with probability 2/3. And t low equals 100 with probability 1/3. Okay. So that's the assumption. Now, what would we do? We apply similar idea like the original continuum of action that we had before. We try to maximize the payoff on the value that each herder will get, and at the end see where they meet or intersect each other in order to find the Bayesian equilibrium. Okay? So for any type T, no? And rival strategy. Rival strategy, what is this now? Q2, right? The number of chips that the other player wants to have. Herder one would want to maximize the value, the total value he gets, which is the best response function also. Remember, last time we have that, we showed that the best response is determined by the maximization problem with respect to Q1. Now, Q1 times the value per chip. Now, V1, which is a function of Q1, Q2, and T. Now we plug in the function. Q1, Q1, V1. Let's put it here, bracket here. T, now, minus Q1 minus Q2, because we open the bracket here. Okay. First order condition, standard procedure for maximization problem. The derivative of the max, let's say U1, okay? U1 with respect to Q1 equals, now taking the first derivative of this term, Q1 times T, so derivative will be T. Now, the next term is minus, because here we have minus Q1 squared, so derivative will be 2Q1. And then another minus, so that will be minus Q2, right? Equals 0. And then we could rearrange already to solve for Q1. Remember? Sorry, this is 1, not 2, no? 1. Q1 equals T divided by 2 minus Q2 divided by 2, right? Let's give it a box first, because we may need it later, all right? I would also write an equation number over there. Okay. So now, if you substitute T with TH, T high and T low inside, we would have, let's also say Q1 high equals T high divided by 2, 130 divided by 2 is 65 minus Q2 divided by 2. Yeah. And Q1 low equals T low, type low, 100 divided by 2, 50 minus Q2 over 2, right? Another box. Just save it for later use. Now, so that is 2 and that is 3. Okay? So that is what we get. And this is what the reason why you have learned before that it has direct and indirect effect on the strategy of on the payoff of the player, right? So it affected Q1, and it's also affected T over here, the direct effect. Now, so that's the first thing. Now let's calculate the expected payoff of the 2. Why expected payoff? Again, because the 2 is uncertain about the type of the 1. So he has to infer from his belief given by the probability distribution. Now, expected payoff is, first of all, probability inverse 2/3 times the payoff when he faces the high type of the 1. So Q2 times V2 120 minus Q1 high, right? Because we concerning with the high type first, minus Q2, that is the total value when he faces high type, plus 1/3 the other probability of T low. Now Q2 again times 120 similar, but minus Q1 low, right? Minus Q2. So just to make it a bit clear, if the 1's high type, he faces this payoff. If player 1 is low type, the second hurdle will face this value, total value of payoff. And then, because uncertainty, we have to weight it by the probability of the 2 scenarios in order to arrive at the expected payoff. That's the idea. Okay? So we could again maximize this expected payoff max EU2. This is EU2. This is like that. Okay. Equals. Now let's simplify this a bit. Okay. So you have 2/3 Q2. Here you have Q2. The other term you also have Q2. So let's put them ahead now. Times. Factor out Q2. What do we have? 2/3 times 120 plus 1/3 times again 120. Let's go first here. So 2/3 times 120 because Q2 is here already now. 2/3 times 120 and 1/3 times 120 return to 120, right? Because you could also factor out. Let's put a box somewhere here. For example, 2 plus 1 is 3/3. Sorry. 120 equals 1 times 120. So that's the idea. Plus minus 2/3 times Q1 high. And because the second term doesn't have any Q1 high, just rewrite it. And for Q1 low in the other term also, but now with 1/3, right? This is here and here. This so far what we do. Okay, and for Q2, the remaining Q2 in the bracket is actually the same with 120 that we did before. 2/3 Q2, 1/3 Q2. At the end you have Q2. This is not a plus, this should be a minus. Okay? Close the bracket. I will be back starting from here. Okay, let's continue. So this is the result that we have previously, and we'll continue further from here. Now, so if I call Q1 bar equals 2/3 Q1 high plus 1/3 Q1 low, then the expected payoff of the other two would be Q2 times 120 minus Q1 bar minus Q2. Right? Let's leave it there. We go from there later. But now let's go up track a bit. By substitute Q1 high and Q1 low in the second and the third equation into Q1 bar. What would we have? Okay, so we have Q1 bar will equals 2/3 times Q1 high, which is 65, right? Minus Q2 over 2. That is Q1 high plus 1/3 of Q1 low. What is Q1 low? Substitute in 50 minus Q2 over 2. Right? And simplify it. Then we would have Q1 bar equal, now 2/3 times 65, so 2 times 65 is 130, right? Over 3, because here we have 1/3 times 50, that means 50 over 3 plus 130 over 3, right? Minus how do you say? Okay, 2/3 times Q2 over 2. Just be careful I don't lost track on that. Okay, 2/3 of Q2 over 2. Here you have another 1/3 of the same Q2 over 2. So at the end you have Q2 over 2. Similar way of thinking like before. Meaning, let's put it here to save space, Q1 bar equals 180 over 3 is 60, right? Minus Q2 over 2. And let's give it another box over here. So this, let's say this is 4th and this is 5th equation. Right? Just keep it there. Now let's derive the first order condition for max EU2 problem. Sorry. So EU2 is here, the first order condition. We would have to take its derivative EU2 with respect to Q2, right? So Q2 times 120, derivative will be 120. Q2 times minus Q1 bar, derivative would be minus Q1 bar. Q2 times minus Q2, meaning minus Q2 square, derivative will be minus 2 Q2, right? And set them equal 0. That's the first order condition of expected payoff maximization. And there we could solve for Q2, which is 120 divided by 2, 60, minus Q1 bar over 2, right? Let's give it another box and number. So that's the equation 6. Now you could substitute the one that we have Q1 bar. We derived it into this expression in order to solve for one of the Q's. No? So substitute 5 into 6. Even though the problem here is somewhat new, but the approach for maximizations very much to the direction that what we have known before. No? So that is, we would have Q2 equals 60 minus Q1 bar, 60 minus Q2 over 2, right? And everything divided by 2 again. Okay? Equals 60 minus 60 divided by 2 is 30, right? So 60 minus 30 is 30. Minus times minus, meaning plus, right? Q2 over 2 and divide for another 2, so Q2 over 4. So now we have Q2 on one side and 30 plus Q2 over 4 on the other side. Let's continue, meaning we just put everything with Q2 on one side. So Q2 minus Q2 over 4. On the left hand side, what will we have? 3/4 Q2. And on the right hand side, we have 30 along. At the end, we will have Q2 start, already denoted by star, because now we have a final solution for it. 30 times 4 is 120 divided 3 by 3. So that would be 40. Done with Q2. Okay? So now we have Q2. We could plug in back to Q1H, Q1L to find these two numbers. And we're almost done over there. So we could plug in Q2 start, 2, 3, and second and third equation. We would have let's say Q1 high equals 65 minus Q2 now is 40 divided by 2, which is, let's write it again so that I could give it a box. So Q1 high start equal 65 minus 20, 45. One box. Okay. On the other hand, we have Q1 low start equals 50 minus Q2, now is 40 divided by 2, meaning Q1 low start equal 50 minus 20, 30. How to interpret this? The thing is, this is how we interpret it. Given this setup and this probability, the belief that player 2 has about the type of player 1, his best response are at the Bayesian Nash equilibrium. He should have 40 ships placed on a common area. For player 1, if he's a high value type, then he should have 45 ships. But if he's a low value type, then he would only have 30 ships at the Bayesian Nash equilibrium. That's the interpretation. Next, last thing, we go with the graph. Okay, final thing. Now let's graph the best response function on the graph. Okay? So do you still remember what's the best response function with a continuum of action? Is the function of Q with respect to the Q of the other order, right? You derive from the first order condition. So this is the best response function of order 1. And this is of order 2. Now, so we graph all of them on the graph. So the Q1 bar we forgot to calculate, or I forgot to calculate previously, so let's put it here. Q1 bar, like the average, star would be here, you could calculate that directly 60 minus Q2 star 40, right? Over 2, which is 60 minus 20, and at the end you have 40. Okay. So now let's graph. Okay. We have Q1 on one side and Q2 on the other side. Q1 now let's graph first Q1 high. So the first intercept would be set Q2 to 0, then Q1 high is 65, right? So I would just split it here. Okay. Here is 130, here is 65, right? And here similar, not really straight, okay? But anyhow, let's use your imagination a little bit. 65, 130 here. So this is the first point. The second intercept, I showed you last time, right? Set Q1 edge low equal to 0. Edge, sorry, not low, but high. No? Then you solve for Q2. So Q2 would be 2 times 65, 130. So this is the 2 point. To graph the Q1 high. Let's see if I can make it. Pretty good. Okay. So this is Q1 high, right? How about Q1 low? Similar, the first intercept would be 50. Now, 50. The second intercept would be set Q1 low to 0. And then so for Q2, 50 times 2, 100. 100. Okay. If it's parallel, then we're successful. If not, then not. Not really, but not bad neither. Okay. So this is Q1 low. Now, need to change to another color. Because I have a lot of color. Why not? Okay. Then Q1 average. 60 minus Q2 over 2. Similar reasoning. I could have 60. So somewhere over here. Not in the middle, nah? Must be closer to 65. Makes sense? And then shouldn't use this one, but another one, maybe. Let's use this one. Okay, 60 and 120. That would look like. So here 100 20 again must be closer to 130, so let's move it up a bit. 120, and there is 60. Now it's not really straight. Yeah. Just have to bear with it because it's impossible to navigate like precisely on this classboard. Okay. Let's put it. There. So this one, the line in between is the Q1 average. So now Q2, that response of Q2. This is what we derived from the first order condition of maximizing expected pair of hurdle 2. So 60, a bit here, lower, and then the other intercept would be 120. Obviously not straight. Okay, so questions. Now where would they cross on the graph? This point where it's cross Q1 average, and Q1 average must be 40. At least it's to the left of the 50. That's already a success. And the best response would cross Q2 at 40. Remember we saw for Q2? Q2 start equal 40, right? Q1 high start is 45 and Q1 low start is 30. So this is Q1 low 30. So it's cross this best response of Q1 low at 30 and cross the best response of Q1 high at something in the middle of 40 and 50 over here. But it's just too dense to write something there, so it's here. Imagine that, okay? So that's the best response function on the graph. We through with game theory. It was tough, I know that, and also probably not easy for you guys with all the especially complicated thing with expected payoff and so doing it by yourself with my video. But yeah, at least give it a try, and you could try again in a live session next week.